A 3 kilogram slice block B, which is initially moving to the left at 1.2 meter per second on a horizontal rail guide, is pulled by the force P 50 T Newton and is resisted by the force FAB 20 Newton as shown, where theta is arctangent 3/4. Determine the velocity of the block at the end of 2 seconds and B, the corresponding force exerted by the block on the rail guide. So you have a collar B pulled by a force in this direction theta. Even it moves, the angle theta will remain the same. At the same time, there is another force P, which is 50T. T is time. It means the force P is not constant. It is depending on the time. And then there is a friction 0.2 for kinetic. Between static and kinetic, when we deal with a motion, the friction will be kinetic. When we deal before motion, it means still at stop, we use static. Usually in this dynamic, we use kinetic. The velocity of the block at the end of 2 seconds. Question 1. So let's put the direction. I assume positive to the right, positive upward. Now I draw 3 diagrams. We are going to draw the initial momentum diagram, and then we draw the impulse diagram, and then we draw the final momentum diagram. Let's see the initial momentum diagram. Momentum is mv. It's stated that B is moving to the left, 1.2 meter, and then it has mass. So the momentum is mv1, directed to the left. That's the only one. Let's see the impulse diagram. First, there is a force. And then there is P. There is the weight. I multiply each of the force here with delta T, or I integrate with dt, because I'm drawing impulse. So here we have, since FAB is constant, the impulse in this direction is FAB times delta T. The weight is directed downward. The impulse will be W times delta T. Here the P, I don't multiply with delta T because P dependent on time, 50T. So I need to integrate P dt. We have the reaction from the rod to the collar, which is N. N is the reaction force. The impulse will be N times delta T. The direction of the arrows follow the direction of the force. So by right, the impulse diagram is just like the free body diagram, except you include the time. Let's assume that at the end of 2 seconds, block B already moves to the right. So you can put assumption it's still moving to the left. Later you see whether it is correct or not. Why I need to assume this one? Because I need to know the direction of the friction. If it moves to the right, the friction will be to the left. If I assume that it's still moving to the left, the friction will be to the right. So here I put F friction times delta T. So now you have the impulse diagram. See the final diagram. Since it moves to the right, the final momentum diagram will be to the right, mv2. So you have the 3 diagrams. As a matter of fact, you just add in each direction. I write the equation. I will focus in the x direction because the motion is in the x direction only. There is no motion in the y direction. In the vertical direction, we have equilibrium. The collar doesn't move in the vertical direction. It means the sum of all forces in the vertical direction is 0. I have negative W plus N negative FAB sine theta equals 0. After you obtain N, you can calculate friction force. You know that friction force is mu times N. You have the value of friction. Impulse due to force P. 50T, you integrate, it becomes 25T squared. between 0 to 2 seconds. So you have 100 Newton second. So we turn back to our three diagrams. In the x direction, you have all the values. The only thing that you don't know is V2. So you have V2. The corresponding force exerted by the block on the rail guide, so that is the normal force. We have calculated the reaction force from the rod to the collar. That is the reaction force from the rail to the block. The force from the block to the rail, it will be the same magnitude but opposite. So you have a value 41.43 Newton but directed downward.